Good morning, everyone. Welcome to our talks. I think this morning the two keynote speech is very good. I like it very much, and I completely agree with Rena. So human-robot collaboration has a long way to go. So at least at least for the next 20 years, our job will be safer. So okay, so let's start it. So our talk today is natural language situated dialogue by me and my colleague Rijie. We are we are from HLT lab in NUS. And the agenda for today is I will give an introduction on what is natural language situated dialogue. Then my colleague Rijie will give a talk on speech recognition, followed by summary. Then the Q&A session will be, I think, on the panel discussion. So look at this one. This is a dialogue system, two dialogue system. On the left one is a normal dialogue system for robots. You can see that it's very hard for the user and the robot to collaborate, especially when there is interference from the environments. In this case, the system mistaken a command from another speaker in the background. And while on the left, you can see that in ARSD system, the user and the robots are able to actually collaborate more easily to get the task done, even when there are interference from a second speaker. Actually, the system is able to recognize it and respond accordingly and reject the command, and the dialogue flow go through, and the task get done. So, but look at this graph. It shows a typical dialogue system built with speech technologies like speech recognition and the TTS, and with some NLU modules. But we know that it's very hard to build high quality dialogue systems. Those are some of the challenges we're facing, and you need a lot of labor data to train the system. And also, once your system is set up, sometimes you need to change the flow, the dialogue flow. Also, you need to change, maybe add in some business rules. This will be sometimes we need to refactor the whole system. And also, we know that the user sometimes they doesn't respond in a fixed way, so they make mistakes, causing exceptions. So the dialogue need to be flexible and resilient to cater for these needs. And also, we in the example you also see that we need a speaker recognition to actually to able to reject the interference from the environments. And we know that speaker recognition is very hard to generalize from one population to different populations. So we propose our NLSD system to tackle all these challenges. To build a NLSD system, we have two steps. The first step we call the system at the design, where from the left you can see that we have the dialogue generator. With the help from dialogue evaluation and the dialogue summarizations, it's able to generate some high quality candidates for the dialogue system to choose from. Then the dialogue system will execute the dialogue flow and generate labeling data. So basically, we are setting up a trial run system to run the input from simulated user and also text to speech to collect data. After a while, once we collect enough data, we use this data to train the system and refine the whole system. Once the system is able to perform to some acceptance levels, we're going to into the second stage. We call the system at execution. At this stage, the real user will come into play, where we continue collect label data and unlabeled data. And then this whole process is iterative and highly automatic. So you can keep on improving the system to keep on improving it. So that's roughly what NLSD system. So next, my colleague Rijie will talk about how to tackle the speaker recognition challenge.
Okay, thanks, Chunlei. So today I want to introduce something about the speaker recognition. So firstly, what is speaker recognition? We know that when human beings in the daily life, actually, we identify the person by the different modalities. For instance, for face recognition, we can know who you are. And similarly, different people have the different voice characteristic. So people can also know the identity of the specific person by its speech or the speaker identity information. So based on that, actually, robot can do the similar thing because you do not want to robot to listen to every person or the every people. So if we not want to know the specific people's voice, we have the speaker recognition model. For instance, if there are multiple people and we want to know who is it, that is a speaker identification. If today we get two utterances and we want to verify whether these two utterances come from the same speaker, this is a speaker verification. So in this task, we propose a task is self-supervised audiovisual speaker recognition. So firstly, what is audiovisual speaker recognition? As I just mentioned, people can know some identify or some person based on the speech, can also know these people based on face. So actually in the daily life, when we meet some person that you already know, you actually based on these two modalities to identify some person. And but there is one problem. When we have a speaker model or a face model, we usually need a large quantity of labeled data, which means for speaker A, we have 100 videos. For speaker B, we have 200 videos. Then we train a classification model. However, this model can only work in the specific areas. Like if today we use these kind of recording devices, we collect a large number of data. So if we change this mode, if we use this model in another scenario, like use a different kind of recording devices, this model cannot work. So based on this condition, we propose a task is self-supervised learning, which means today in the website, we can get a large quantity of video like this format and use the face tracking and face detection model. We can have this kind of, we name it talking face data, which means there is one people on the screen, you have its face and its speech, these people is keep on talking. And our problem is that can we learn a speaker recognition model and a face recognition model based on this kind of data? Because this kind of data is unlimited. You can get many this kind of data. So based on that, our proposed baseline is a multimodal contrastive learning framework. So it's similar to the original contrastive learning framework. Let's say we have one video and it has a speech part and it has its face part. They come from the same person. So for the face part, if we want to learn a face model, we select the two face from this video, and we will then come from the same person because it's the same video. And for the speech part, similarly for one utterance, we select two segments. They come from the same person. And then today, if there is another video, so for the two segments from the different video, we will then add the negative pair. So what does it mean for the positive pair and the negative pair? Because the positive pair come from the same person, so we hope this distance can be closer. And for the negative pair, because they come from the different person, we hope the distance can be far away from each other. So based on that, we train this model, and finally we can get the speaker encoder and the face encoder. And this cross-model system is also used to optimize this distance. So finally, what we get is this speaker encoder and face encoder to identify the people. So this is our baseline. And here we propose a research problem. So this contrast learning method can solve the unlabeled issue. However, is this contrast learning selection method is really perfect? So let's say I give you an example. Like today, I have one labeled data, right? This is one video, and it has the face part, it has speech part, and we select the two speech segments. We view it as the positive pair, but I name it as a poor man's positive pair or naive positive pair, because we consider several scenarios for these two segments. So firstly, for the speaker information, these two segments has the same speaker information. That is what we want. However, for some other issue like the acoustic environment, like the BGM, like the noise, these two segments is also the same. Like the speaker status, the decision topics, recording devices in these two segments, they are all similar. So in this condition, when model learns this is a positive pair, it did not learn the meaningful information. The meaningful information here is the identity information. It may learn some other information like it learn the noise is similar, so this is a positive pair. So in that condition, the result will not be so robust because it did not learn the meaningful information. So similarly for the face part, I can give you an example. Like today, if you want to see these two are positive pair, actually it is very easy. You do not need to know that they look same. You can only know like their clothes is the same, the background is the same, their pose is the same. But if model knows this kind of information, actually it did not load the know the face representation information. That is a problem. So based on that, we propose the motivation is that better positive pair selection is important for self-supervised learning. For instance, if today we have one video and we have its speech part and the face part, and today if we have another video, they come from the same person. So we select the two segments from these two videos and the two faces from these two face part, and we will them as the positive pair. And we come back to the problem we just mentioned. So for the speaker information, they are still the same person. That is what we want. Well, for the acoustic environment, the first video is an indoor video and the second is an outdoor video. So model will not learn this to verify that this is a positive pair. Similarly, for the speaker status, decision topics like the emotions are all different. So in this condition, if model still need to know that these two segments come from the same person, it can only learn one thing, is that the speaker characteristic or the voice characteristic is similar. So that is what we want. Similarly, for the face part, you can see these two faces, the color is different, the background is different, so it can only learn that the face representation is similar. So based on that, our proposed model looks like this. So the right part is the same. The difference is for the left part, the sampling technology. So when we have an anchor video clip, we did not select two segments. We only select one segment and one face. Then assume we have a positive video clips like a library. All this data comes from the same person to the anchor video clip. We randomly select one as the positive video clip, and we choose the face part and the speech part as the positive pair. That is the difference. The next problem is that since we do not have the label, how can we know that these two videos come from the same person? We propose a method is based on the clustering approach. Clustering means we have a large quantity of data and we divide it into multiple clusters. However, this is not easy because we do not have a robust representation and we don't know the number of clusters. However, if we have two videos, multiple videos from two speakers, like this is representation, and today we do the clustering for 10 clusters. So same cluster, same color means the same cluster. So from the clustering, this result is totally wrong because you only have two classes, but you have 10 clusters. However, if today this is anchor data, and in this condition, all the positive pair is these blue dots. So you can find that a large number of clusters leads to a wrong clustering result, but it can guarantee the anchor data can find some of the correct positive pairs. And if we reduce the number of clusters to 5, we can find the anchor data find more positive pairs, and the new found positive pairs are more diverse and can benefit the system. So that is what we want. Based on that, we propose this colloquial learning method, which means in the beginning, the model is very weak. So you give it a very easy task and it can learn and improve. And then in the later stage, the model becomes strong and you give it a harder task. So here we, in the beginning, we choose a very large number of clusters. Let's say if today we have 100 videos, we divide it into 100 clusters. So one data is one cluster. So in this condition, the model come back to our baseline. And then if the validation performance cannot improve, we divide the number of clusters by 2. So in this condition, model have to remove more and harder diverse positive pairs to the anchor data, so it will improve the performance. So finally, we see some results. So compared with the existing self-supervised method, when the test modality is speech, we report the ER on 3 different data sets, and the ER is lower is better. So we can see compared with the previous work, our method get a large improvement. And we also report that if we use the face modality or speaker and the face modality together, the ER can get very low. And all these experiments, we do not use any identity label. So finally, we report these results. So usually, even people do the self-supervised learning, they use a large scale to label the data, and they assume that they did not use the label. So actually, this is not interesting because although you did not use the label, you already know the data set is very balanced or how many speakers in this data set. So in this experiments, we can see these 2 lines. We do the experiments on LS2 and LW. These 2 data sets actually is for audio-visual speech recognition, which means that it's a real unlabeled data set. Nobody knows the speaker identity in these 2 data sets. We can see the blue bar is the baseline and the red bar is our proposed method. In all the condition for speaker recognition, face recognition, and multimodal recognition, our proposed method can outperform the existing method. That can prove our system can perform well for the real unlabeled condition. So that is all from my work. Yeah, thank you.
Yeah, to summarize, is it? Thank you. So to summarize, our AISD starts with some pre-trained NLU modules. Is generate labeling data for finding, tuning the system. Then it's easy to adapt to some new dialogue, and it's keep on improving itself so that it can achieve high user acceptance. And also with speaker recognition, you not only need able to recognize command and intention, you also can recognize the speaker to cater for some more broad usage scenarios. I think that's all for our talk. Later we have a session. Thank you.